Welcome to this final module of the course, where we tackle one of the most critical yet often unexplored aspects of spatial energy modeling: how to obtain meteorological data that is both accurate and spatially detailed enough to inform energy decision at the local scale. In the previous modules, we worked with spatial data layers, GIS tools, and planning workflows. Now, we take a step back and examine a foundational input to many of those analyses: the weather and the climate data themselves. The central issue is that the meteorological data available to us, particularly those coming from reanalysis or climate models, are typically produced at very coarse resolutions, ranging from 25 to over 250 kilometers. That is acceptable for global climate projections, but completely insufficient when planning energy infrastructure within municipalities, industrial zones, or even individual sites. This is where downscaling enters the picture. Downscaling is the set of techniques used to refine coarse-grained climate or weather data into high-resolution surfaces that reflect localized conditions. These downscaled datasets enable energy analysts to work with realistic inputs for solar irradiance, wind speed, temperature, and precipitation at the spatial scales required by actual projects. In this module, we will explore the architecture of global and regional climate models, differentiate statistical from dynamical downscaling methods, examine spatial interpolation techniques, and conclude with best practice for visualizing and communicating downscaled data in the energy planning context. The meteorological data most commonly used in energy analysis are typically generated by global climate models or global reanalysis systems. While these datasets are invaluable for understanding atmospheric patterns, they are not directly usable for site-specific energy planning. Their spatial resolution is often from 25 to 50 km or even more, far too coarse to resolve the complexity of terrain, land cover, or built environments that influence wind, solar, and thermal conditions. For instance, when selecting a site for a wind turbine, it matters whether the location is on a ridge, a valley, or a flat plain. These features might be completely invisible in coarse climate data, yet they have a substantial effect on wind flow and turbulence. Downscaling allows us to refine these inputs. It provides a translational step that turns global climate knowledge into actionable local insight. This is critical for ensuring that our energy models are not just scientifically sound, but spatially relevant.